And today we will be going over the overview and evolution of our most recent robot, Phoenix.
Okay, so just to start us off, we're going to talk about what we ended up with, so y'all know kind of what's in reference, what we're referencing. We have the robot here, and I know there are a lot of lines, and it's pretty confusing. But if you break it down, it's kind of simple. Each arm is on a turret, and it has one large pivot, an extend, a last pivot, which we call our third pivot, which you'll learn why. Our wrist, which turns like this, and our grabber. And that's the basic overview. And then, of course, how can we forget our drivetrain extends, which are, I don't think this is, oh, it's right. And so that's the basic overview of what we're talking about in general. Yeah.
Next slide, please. For our first robot, Valkyrie, this robot gave us a lot of insight and it helped us set a lot of goals for our most recent design. For Valkyrie, there were two main topics I'm going to focus on: cycle time and junction accessibility. So with this design, we had generally slower cycle times, and the three things that helped contributed to that was our intake, our cycle, and the fact that our intake was on an extension. So for Valkyrie, our intake utilized two claws on a linear bearing that would close in on a cone. And this cone would then be retracted on an extension that would then be transferred into an inner cone grabber, which was on a turret that finally scored on a junction. Now, this design was not only complex, but it didn't serve the right purpose of keeping the most simple path of the cone to the junction. And this was a large point that we learned from, especially from our lead meets. The second point I want to talk about is our center of gravity. For Valkyrie, it was very lopsided, and it was obvious to the drivers, especially during practice matches and the real games, that it wasn't consistent in where it was driving. Finally, junction ownership and accessibility. For this robot, our play style was to sit in a square where junctions were surrounding it, and our intake would extend to the substation, intake a cone, retract, transfer into an inner cone grabber, which was mounted on a turret, and that's what scored on the junctions. As you can see, as you may understand, this is a very complex process, and the transfer was a step that we understood wasn't consistent for us. And that's why we decided to go to a more a design that emphasized junction accessibility.
Okay, so as Sophie explained, on our arms, there's a linear extend that allows the arms to extend. But before we reach to this design, when we first initially designed this robot, it had a second pivot that was right here instead of the linear extend. Some benefits of these were that, again, we have that faster cycle time, and we had more reach than we did on our old robot, Valkyrie, which allowed us to get that, or a potential 1+10 auton. It was more consistent, and it allowed for a more adjustable husky aim that was not possible with our old Valkyrie robot. But some of these problems that we faced with it was that there was a lot of backlash in the pivots, which allowed the arm to shake a lot. So when we went to aim towards a pole, it would not be as accurate each and every time. Another problem that we faced was that the arms themselves would hit each other so many times, or really one specific time during a match. When our drivers were going towards pole, one was coming back to the substation, one was aiming to a pole, they actually clashed within another, and we had to stop playing that match. So obviously a big issue that we faced, which is exactly why we switched to this linear extension arm, which gives us that reach that we're looking for and that kind of simplicity so that the two arms don't hit each other.
So once we decided that we're going to move to what we call our robot Phoenix, with this two-arm design, we still obviously had improvements to make. The most significant one being going from a second pivot to these linear extend, which are, by the way, servo-driven. A lot of people are shocked that we use servos for that extent because of how fast it is, but it's just a rack and pinion. But we still had some problems we wanted to fix from that bent arm. So like Rita talked about, one of the biggest issues we faced with that iteration of the robot was the amount of backlash that we had in both this first pivot and the second pivot that doesn't exist anymore. Because when we were here, without this could move about like, I don't know, an inch and a half, with all the servos thinking they're in the wrong spot, and the backlash wasn't consistent either. So it wasn't something we could correct for in programming. So what we ended up doing, we got rid of the bent arms and replaced so these slides, and we also took out the driving axle, or the driven axle, I think, on this large gearbox, our first pivot. We took it out, we added JB weld, and put it back in to tighten up the tolerances of the key slots that it was locked in with. The linear extend was also faster and more stable, and it had a smaller profile than the big clunky arms. And then there were still some issues with this iteration that we wanted to improve on. Our strategy at this point was we would sit outside the Alliance Station, where they put the cones. It's been a while since we played. And we would extend the arms into the substation to grab a cone. But that was still a little slow. And so one thing we wanted to do was have a grabber that opened all the way up. So we could sit right outside the substation. Human player could put a cone out. We could grab without having to use these extends. And then we also just wanted to have better and more consistent autonomy.
Some additional improvements that we made when we designed this robot was our claws. So we went through a bunch of iterations with our claws, but the one that we set on is a 135-degree claw. Basically, what happened when we have this much extension is we don't want to be have a slow cycle time, especially when picking up from the substation. So instead of having to extend out every single time, these claws allows it so that when they're open, we're just sitting right in front of the substation. So we're not technically in the substation. So a human player can still place a cone. And then when the claw closes, it just makes for faster cycle times. Another improvement we made was guides for autonomous. There are these plates here. When we first started, we used the Husky lens, and they were accurate, but they weren't as precise or accurate that we needed it to be. So these guides just helped a lot with aiming. And then we also have something called lane mode, which is something that we use with teleop. So instead of sitting stationary and just behind a pole, we would go up and down a specific lane, and we could change lanes as well so that we get more reach and more ownership over the pole.
Thank you.
Okay, can y'all handle the raffle?
Anyone have any questions?
Can y'all handle the raffle? You're in charge of the raffle. I have to leave and talk to Shook.
So Husky cams, but did you use them with the whole guide or did you get rid of them entirely?
So
sheets.
because of the way our arms scored in
Just write it down.
so
online
for autonomous, because we flipped over to score, and so they would hit the they would hit the does that make sense? They would hit the back of it. But in teleop, we always scored with this, and you see this little box that used to house our Husky cameras. So they would aim, and they would be color sent to the poles for that. So we could use them both. We found that it was the Huskies just simply weren't fast enough in the end, and so we went for the guides instead. Any other questions?
Yeah. All right. Kyler from team 8641 online asks, how do your drivers control which pole the arm goes to?
So driving was, I don't want to say easy, but it wasn't as complicated as you might think it was. So we're the two drivers that drove this robot, and the way we split it up is we both got an arm. We split custody of this robot, and so we had a preset. Each controller. So my game had one, and her game had two. Each button would bring you to a different pole, and we had shift buttons. So we have a high one, a high two, and a high three, and a mid one, a mid two, and then a low one and a low two. For each gamepad. So that meant this arm had all those presets, and this arm had all those presets. And so that's how we controlled that. And as for splitting the drivetrain, we just had a special button that said, I want my half to go left, or I want my half to go right. With the joystick.
So I saw you guys extend your robot. So when do you use that?
So we've needed to use it the most actually for something we didn't anticipate. Rolled a couple times. An opponent dropped a cone into our robot, and though it wasn't a penalty, the refs were confused, and that's all right. So we split and we strafed over the cone. to get it out of our robot. But we also had different positions in the beginning of the season. That, as Rhea said, our first spot was to just sit behind that center pole, but we also had an option to extend out and sit like over the center two tiles, if that makes sense. Anyone else?
So I've seen that you're able to use sidewalk to move it up and down, that is in the system, right? Also taking the weight and use it to move it. If there is something.
Yeah.
Yeah, so for extension, we are using this Go Builder motors, or servos, sorry. And the extent and our goal for the our scoring mechanism at the top was to keep it lightweight. We actually had multiple mentoring sessions with SpaceX talking about how to limit the weight at the end in order to decrease inconsistencies in wobbling that you might expect from this.
Yeah.
So it just wasn't that heavy at the end. I mean, it was, but these servos, we use 5-turn super speeds from GoBuilda and set position. So they just held their position. We had issues. One issue we faced with these linear extents, we didn't realize why the servos started burning up. Funny story. If you see this metal reinforcement on the back of this slide, it's tiny. I don't know if y'all can see it from back here. This one, that little metal reinforcement was because we realized the slides were actually starting to bend because of how long we would hold them out here when practicing, or we would be moving the arms while they're extended. And so that general like lever arm was really taking a toll on this slide specifically, and it would bend. And so once we figured that out, we added reinforcement and had to replace that one servo that burnt out. But they support the weight really well.
Do we have any more questions? Any more questions from online folks?
He has a question.
Slide.
They're the Misumi 2-stage, 300 millimeter.
And how fast can your slides go actually?
Okay, with them.
Our cycle times are like, I believe, 5 seconds.
There were 4 when we were on a really good battery.
Yeah.
I don't know. I would guess from totally retracted to fully extended. Patrick told me this is wild. 0.8 seconds?
That's about what I would guess all the.
0.8 seconds is a guess. That's not like we could calculate it with a JVM calculator, but I don't have that on something here. Okay, well there are no other questions from online. Oh, I'm so sorry.
So are most of the or all of these that you use GoBuilda?
So we split between a lot. Our drivetrain is really a GoBuilda straight for chassis, split in half. Connected with slides. We use revs and we have a lot of custom parts too. All the motors I think are GoBuilda though. I don't know. We don't necessarily stick to one brand. We see what is gonna fit whatever we want to try to do. But I think there's a lot of GoBuilda on. Yeah.
All right.
Okay. Cool. Thank you guys so much.
Cool.